So we will start with, first explaining what is a language model, because that is very important to understand how we have these models capture knowledge about the world. So first of all, what is a model? Suppose you have data, any type. In our case, we are talking about textual data. So we want to have a system that models the data. What do you mean by that? It means that system, suppose we use the system to generate data, it will generate data which is similar to the data distribution that it has seen. For example, if you want to generate image data, say data about photographs or data about paintings. So you have a set of data on paintings or set of data about photographs, and you have a model which learns that data, and it is able to generate new data which is coming from the similar distribution as the data it has seen, but it is new data, right? So this is about, we have heard a lot of terms nowadays. So this is about one of the terms that you might have heard a lot, which is called generative AI. Generative AI, you try to model data which you try to generate. Now let us come to text. Let us say we want to model language, so that we can generate language or we can use certain properties of that. And for that, we want to model the language. And one of the simplest way to think of how we model language is to say that sentences or sequences that belong to the language, that belong to a language. You see, a natural language, we can formulate infinite number of sentences, right? We want to model language so that those sentences which are likely to be correct, good sentences, they have high probability. A simple example that I have taken is from the domain of speech. Suppose in speech recognition, you have a set of sounds that you hear, that you get. We call a set of phonemes. And then based on this set of sounds and based on your understanding about the language, you try to find out what is the best transcription of those sounds. For example, if you see those two sequences, they may come from the same set of phonemes. But since we understand this language, we know that I saw a bus is more probable that I saw a bus. Okay. So this is because we are able to model language. And there are some very simple, examples of systems which model language. For example, for a long time, even in our earlier versions of cell phones or emails, you want to predict the next word, or you want to complete the sentence, fill in the blanks. These can be done easily if you're able to model language. Now, we want to, in order to do these tasks effectively, we want to have language models. And these language models get trained from actual language. And the main source of knowledge here are pre-trained language models. These pre-trained language models, they are trained on huge amount of textual data. That is what gives them power. Okay. Now, once we have these pre-trained language models, and they are modeled from huge amount of textual data, so we call them large language models. And sometimes people also refer to them as foundation models based on their capabilities. Which is, I'm just putting a lot of terms, please excuse me, and they say it is part of GAI. Anybody can say what is GAI? General artificial intelligence. Earlier, people used to say that humans have general intelligence, whereas your AI systems work on specific tasks. So they have very specialized and narrow domains of intelligence where they work very well. So we want to have a march towards general AI. And for this, we have foundation models. And in many cases, these foundation models are built out of very large language models, enormous language. Okay. And they are pre-trained. And in order to do the pre-training, we want to train them from unlabeled data. So we have using self-supervised learning. Which is a euphemism of unsupervised learning, because we don't have any labels. We have unlabeled data, which we pose as supervised learning. We already seen example of semi-supervised learning, self-supervised learning. When we talked about word to vec, we said from the surrounding words, guess the central word, or the other way around. We do something like that here. Now, so for this self-supervised learning, we have to set up some learning tasks. And these are examples of some of the learning tasks I will describe. There are others. So one of the successful models of these large language models was BERT, which was from the Google team. And this used certain, pretext tasks. One of the tasks was masked language modeling. What is masked language modeling? You take a sentence and then randomly you take a fraction of the words and you mask. And you let your model predict those masked words. Anyway, so you get your model to predict the masked words. So suppose you say, how are you doing today was the original sentence. You mask this word and you try to predict this word. And based on whether your model is able to predict the actual word which was masked or not, based on that, you score your model. Right? So this was the basic idea. And there are certain fine prints that, for example, in the BERT model, they randomly took 15% of the words and masked them. And actually, they did not mask all of them. 80% of the time they masked, and sometimes they retained it. So there are some fine things that we'll not talk about. This is the basic idea. The other thing is that, people who study machine learning or deep learning, they will be aware of different types of deep learning architectures that have been used or that have been popular over the years. I'll just mention the names. So deep learning stands for deep neural network, which has multiple layers, right? And depending on the domain and depending on the time period when they came up with, there have been different types of effective architectures. For example, convolutional neural network is very popular when the input is of image. It can be used for text also. Then people use recurrent neural network. Recurrent neural network when they have sequences such as language, and efficient versions of recurrent neural network such as LSTM or GRE. And then around 2017, they came up with 2014, they came up with attention models. And around 2017, they came up with this transformer model. Which solely is based on attention. Now, attention could be used with RNN or with CNN, but transformers are models which are solely based on attention. So what is attention? Suppose you have a sequence. So your text is a sequence of words. If you have an image, it is a two-dimensional sequence, spatial sequence of pixels. Suppose in your text, you have a sequence of words, W1, W2, W3, Wn. So this is an input. And we want to get, in my deep neural network, I have multiple layers. And through these layers, I want to get a more and more abstract representation of the input. So that we can, if I have multiple layers, together I can get a very good representation of the input. So in attention, what happens? Suppose it is the first hidden layer, and you have the representation of all the words in this hidden layer, right? So each of these representations is based on the representation of all the words in the sequence in the previous layer. Then you have another attention layer. This is called self-attention layer, where you have now the next level representation. And each of them is composed of the ones in the previous layer. So when you have multiple layers, like 8, 10, or 12 layers, you build upon the previous layers. Now, these attention models, which were introduced first in a paper by Devlin et al., the title of the paper was "Attention is All You Need," became very successful. And many of the large language models have used this, many or I'll say all of them, have used the attention architecture. Right? They could have also used the RNN architecture or CNN architecture. Happens to be that they use the attention. Now, we have to, now when we use these models, which I will come to, you have to feed the text into the model. So how do you feed the text? So first you tokenize the text, right? And then for every token, you put an embedding of the token. The embedding could be one-hot embedding, or it could be more likely the word-to-vec embedding. Is that okay? Any question? Is there something which yeah. I mean, you are building the model, supposedly. You know, Google could have built the model, you're using it. But it is we are building the model. To think like that, yes. Your model will train to learn the embedding, or somebody has trained the embedding and gave it to you, you use that embedding. Any question? If you look at this sentence, my dog is cute, he likes playing. What do you see? Any observation? These are two sentences. We'll come to that. So this is two sentences. And because there are two sentences, we have a token which separates them, separator token. This is the beginning. We put a classification token. This is a separation token. If you look at the word playing, it happens that in my dictionary, there's no embedding for playing. So since I cannot represent playing, I break it up into subwords for which I have embedding. So that's the second. Then let's come to this one. In attention models, I mean, I did not talk about the models, but in recurrent neural networks, you have from position 1 to position 2, you have a link. Position T to position T plus 1, you have a link. In attention models, you don't have such links. So you encode the position of the word in the sentence. So this is the first word, second word, third word, fourth word. For each of them, again, you learn an embedding, like word to word. So this is the position embedding. Now, if you use BERT with the masked language task, you can just use the token embedding and position embedding. BERT is trained on a second task, which is the next sentence prediction task. The idea is that he will give two sentences and he will ask, does this second sentence follow the first sentence? Okay, so he'll give a pair. He will say, in my corpus, is the second sentence following the first sentence? So if it does, then answer should be yes here, or answer should be no. So these are the two tasks on which BERT is trained. And if there's a two-sentence input, then we have a segment embedding. This is first segment, second segment. This is the input to this model. And as I said, in a very abstract sense, so this model is composed of several layers of self-attention. And in each self-attention layer, right, you have representation here, and you have representation at the end of this layer. The representation of second word here is built up of the representation of all the words in the previous layer. That's called the self-attention. And as I said, for training, use masked language model, where you mask certain positions. And then in the mask position, suppose your vocabulary is 30,000 words, right? So you let your model predict the probability for each of these 30,000 words. Ideally, what do you want? You want the word which is masked, that should be predicted with probability 1. So you have a loss, which is the negative log of the probability of that word which is actually masked. So based on this, this model is trained. The next sentence prediction task, as I said, for that we use two tokens, CLS and SEP. CLS is the first position, SEP is the separator between these two sentences. And if the second sentence follows the first sentence, at this first position, you have a linear binary classifier, says yes. So you take a pair of sentences, you randomly swap the order. And 50% are positive, should be yes, 50% should be no. You also look at it. Is it okay? Now, this is done using a very big corpus. And after this, we have this pre-trained model. So what is BERT? BERT is a transformer-based encoder model, which is trained on two tasks, as we have seen, over a huge corpus. And what does that training involve? BERT has several millions of parameters, maybe tens of millions, I forget the exact numbers, different sizes are there. And based on these two tasks on a large corpus, you find the parameter values. That is your pre-trained BERT. Now, this pre-trained BERT can be used for various language processing tasks. For example, you want to have a classification task. You want to say, this sentence is talking about adverse effect of drug. Or this sentence is not talking about adverse effect of drug. This sentence is about cancer therapy, or it's not about cancer therapy. So you can have a classification task. You take the pre-trained BERT, and then for your classification task, you have some labeled sentences, right? For your classification task, you have examples of positive class, negative class, or you have a 5-class classification for all the tasks. So what you do is that at this position, you want to give the class, right? So there are various possibilities depending on how much training data you have. If you have a very little training data, you can keep this language model frozen, right? Only at this first position, you build a small neural network, a small linear model, which has some parameters. With your training data, you only train these parameters. You only train these parameters. Or if you have more data, what you can do is that you can freeze the initial layers of BERT, but the top layers, you can fine-tune those parameters. Or if you have even more data, you could fine-tune the entire parameter. But remember, because these large language models have millions and billions of parameters, unless you have a lot of data, trying to play with these parameters are not very useful. So you only want to play with a small number of parameters. And in many cases, you will not touch this at all. Nowadays, increasingly with larger language models, you only play with this part. Suppose you have a task like information extraction. You want to find the named entities, or you want to fill the slots, right? There, for example, let us take named entity recognition, because that's a very important information extraction task in the biomedical domain and many other domains. What you will do is like this. So you will have a sentence, suppose this sentence, the drug X is used to treat Y. So here X is the name of a drug, and suppose Y is the name of a disease. So you want to have an encoding like this. This is drug, this is disease. Or if it's a multi-word, suppose this disease comprises of 3 words, Y1, Y2, Y3, you will say disease begin, disease continue. So you have an encoding. So, and this is the encoding that you want to identify the named entities. And you will use BERT so that at these different positions, you give the proper output. So this is not part of any entity. So we say outside, O, this is drug, this is O, this is disease. Right? This is what you want to output. So you can use BERT as the general purpose model and then have some small classifiers through which you can utilize what BERT already has, the general knowledge that it already has. And on top of it, you use the adaptive models for identifying these entities. Then let us take a task called question answer. Right? Now, the particular version of the task which I have shown is you have a paragraph, right? You have a paragraph or document. You have a question. The answer is there in this paragraph. And you want to identify the part of the document where the answer is. So begin the answer, end the answer. Okay. So your input is the question, separator, the entire document. And you want to identify the beginning of the answer and the end of it. So if you have some examples of this question answer pairs, you can use BERT and train on this question answer pairs. And given the question, you can get the answer. Last example. This is an example of a general task called natural language inference. So you have a sentence 1, which is the premise, and the sentence 2, which is the hypothesis. And given the sentence 1, you want to check whether this hypothesis is true or not. Okay. So you have a sentence, and suppose your hypothesis is drug X cures disease Y. This is your hypothesis, and you have a premise, which is some text. You want to check whether this is true or not, and you want to put the answer here in the first position. Again, you can train on top of BERT, you can train for this. The point is that this is a general purpose model, which has been trained on a large amount of data, and it encodes a lot of that knowledge, and you can use it for your specific requirements. One of the things that I mentioned was that you often get unknown new words. For example, in the medical domain, you often get new entity names, which you haven't seen before. And in order to work with unknown words, these different language models use different strategies. Some of them use byte piece encoding, some of them use word parts, etc. So this is one example, the word piece in BERT, byte pair in GPT. So basically, what they do is that they identify subwords, including characters. So a word is either fully present, or you can write it as a sequence of subwords. In the worst case, as a sequence of characters. So that you can deal with, because if you look at a biomedical entity, often the shape of the word, the form of the word, gives you an indication of what type of entity it is, and also whether it is similar to some other entity. I'm not going to the details. Now, we have seen that this BERT has a model which is based on the encoder model. So what is an encoder model? You have an input sequence, and you find a representation of that sequence. That's what an encoder does. And BERT is an encoder model. There are two other types of large language models. One of them is the decoder-only model, as we see in GPT, which is basically used for predicting the next word. So the words are sequentially generated. When you have seen W1, you want to predict W2. After seeing W1, W2, you want to predict W3. After seeing W1, W3, WT minus 1, you want to predict W. So if you look at the arrows here, this is a model where you are predicting one word at a time. This is called a decoder model. And decoder models are very useful when you want to generate new data. Because when you generate a particular word, you do not know the future words. You only know the previous. So decoders also use an attention model, but they use masked self-attention, where they only use attention on the previous elements in the sequence, not the future elements. And the third type of model is based on the generalized transformers, which has both the encoder and the decoder. In the encoder part, you encode the input sequence. And in the decoder part, you generate tokens, one at a time. So you use attention here, attention, masked attention here, and also cross attention between the encoder and the decoder. Suppose you have the task of summarization. You have an article, you want to write a summary of the article. We can use an encoder decoder. Or you have a question and you want to generate the answer, not just say this is the start and end of the answer. From the question you want to give the answer, you can use an encoder decoder. So these are three types of large language models which are there. And depending on the application, we use one of them. So for example, this is the decoder-based model. For example, OpenAI's GPT is a decoder-based model. And it is trained on the task of predicting the next. Now, we come to, suppose we use a language model for generation. And for generation, we usually either use the decoder-only model or encoder-decoder. Now, I want to very briefly tell you how we generate using these generator models. So, these generator models are trained to predict the next word, one word at a time. So, how can they be used to generate an entire summary or an entire answer? So there are various methods. In greedy decoding, what we do is that after every word, I predict the next word. I predict the probability of what is the likelihood of each of the possible words. And I take the highest probability next. I incorporate it, then take this next. Up to this we do and take the next. So this is called greedy decoding. Then we have random sampling. We sample the word out of the probability distribution. This is not so useful. And often people do beam search decoding, where instead of taking the highest probable word at a particular position, we look at the k highest probable words. That is my beam. Then the next level, for each of these k candidates, I find k candidates, so that we have total of k square candidate sequences. And out of this k square, we again keep the best k. So like this we proceed. This is called beam search based decoding. Now, I talked about the third type of model, which is encoder-decoder model. For example, one of the examples of such model is the T5 model or BART model. So they are trained on multiple tasks, which has the encoder-decoder part. For example, question answering, machine translation, text summarization, and so on. Right? Chatting or conversational systems and so on. And because they're trained on multiple encoder-decoder tasks, there's a prompt which indicates which task it was for. So this is translate English to German, that is good. Answer is das ist gut. Then COLA is linguistic acceptability, which says that is the sentence a good sentence in the language? For example, you say, the course is jumping well. So this is not a correct expression of saying this. So the answer is not acceptable. This is inference tasks. It says if the rhino grazed on the grass, sentence 2 is rhino is grazing in a field. It says does sentence 1 entail sentence 2? So grass and field, grass, field may have grass, may not have grass. So it's as a score of 3.8. Then the summarization. So these are some tasks on which such models are trained. And while training this, for example, in T5, what they do is that they mask entire phrases. So they take a sentence, they mask certain phrases from the sentence, and put it into encoder. And in the decoder, they want to generate the sentence with those phrases filled in. In BERT, if you remember, we mask single words and we want to predict the next word. In T5 sort of models, we mask entire spans and we want to generate those spans. So this is the landscape of different types of general purpose large language models that we have. And as I have already mentioned, that these are pre-trained language models with model parameter values theta, and often this number of parameters are millions, billions, etc. And if in certain cases we might fine-tune some of them, so we get theta fine-tuned, and in some cases we do not change the model parameters, only change the adapters. Now this graph shows a few of the large language models, and on the x-axis we have the dates, and the y-axis we have the number of parameters. So we see that GPT had about 100 millions of parameters, BERT had few hundred millions, GPT-2, 1 trillion, and so on. GPT-3 has 100,000 millions, so it's growing very fast. So the large language models that people have seen, effectiveness of the model is in most cases does not depend on the clever algorithms that you use for pre-training. Rather, it depends on how large corpus you have trained and the number of parameters in the model. And in most cases, the larger the number of parameters and larger the corpus that you have trained on, they are the best one. I mean, so far what we have seen. Now, with this large language models, we have two types of capabilities. One is called zero, they are related, of course. One is called zero-shot capability. What does that mean? That you take the language model, and in order to solve your task, you design a prompt. You do not give any training exam. You just say, what is the drug entity being referred to in the sentence? Something like that. So you just give a prompt, no training example. And we have few shot capabilities where we give a few training examples to fine-tune the model. Now, apart from these general purpose models, people have worked on special purpose models for specific domains. For example, in the biological domain, they have this BioBERT, there's clinical BERT. So these models are built on top of the original large language model, which is general purpose. And then this is given additional data from the domain. So you tune it for the domain. Initially, you build it on a general purpose domain and then tune it for the specific domain. And the second type of model are pre-trained from scratch from the domain. For example, in biomedical domain, SciBERT, PubMedBERT, Biomegatron, these are examples of models that have been trained solely on the biomedical data. And then people have run different experiments to see, for different tasks that they have, how these models perform. For example, I've just looked at a few papers which are recent. This is a paper, I forget, I think 2022 paper, which shows. So nowadays, when people work on these information extraction tasks, they focus on more on designing the prompt. Right? What prompt you should give to get the correct good answer. So they can manually design the prompt, and in some cases they use machine learning on a given question answer pairs to automatically design the prompt. When you automatically design the prompt may be a natural language sentence, or it could be just some vector, sequence of vectors. So a lot of emphasis has shifted to prompt design. For example, this is a 2022 paper where they explore different prompting on biomedical relation extraction tasks. So they work on prompt design and prompt selection for relation extraction tasks. And they have some results. They show that prompting boosts model performance, both when fine-tuning on the full training set and in a few short conditions. So this is an example. Suppose you have a task, training, and suppose this is the sentence, training sample discovery of novel chemicals, derivatives as genes inhibitors. This is the sentence. And here is a gene entity, and here is a chemical entity. In the traditional machine learning, what we would used to do is that take the sentence, identify the entities, create a dependency parse, and then try to find out the answers. So nowadays, most of the effort has shifted to prompt formulation. So you take the sentence, give the answers, and then you find out the prompts. For example, you against actions of activity inhibited by, etc. So you have some candidate prompts. You can say that you want to design prompts, you can have some candidate prompts, and you can rank the prompts, which ones are better, or you can completely learn the prompts. And you can even do prompt-based fine-tuning. So in prompt-based fine-tuning, typically, you do not change the large language model. The model stays as it is. You try to, these are different answers. You want to design the prompts so that you find out the answer, which is the required answer, gives better results. And as I mentioned, that nowadays, in many cases, people have found in the last 1 or 2 years that they want to make use of these general purpose models, whether it's general purpose or general purpose in the biomedical domain, to find the answers with minimum. Again, this is another example taken from a 2022 ACL paper, where they have this sentence, say androgen antagonistic effect of X, metabolites on wild type and mutated Y. And they have different hypotheses. First hypothesis is chemicals and genes have no relation. Second is chemical is identified as antagonist of gene. Third hypothesis, upregulator chemical is activated by gene. So they have different hypotheses, and they get the model to predict which of these 3 are higher probability. And if they have some training data, on that they train the model so that they can do well on it. This is another paper, 2023 computational links. So nowadays, if you find in the last 1 or 2 years, most papers have shifted to making use of these large language models for information extraction. Before I end, I just want to mention a little bit about ChatGPT. So we have looked at language models like encoder-based like BERT, decoder-based like GPT, and encoder-decoder-based, right? Now, then when ChatGPT was released, many people got very excited because it worked very well. So what is ChatGPT? ChatGPT is basically these language models trained on human-generated answers. And what they do is that they have questions and answers, they have human feedback. And one of you was asking about reinforcement learning. So this is another case where the reinforcement learning with human feedback is the secret sauce that ChatGPT has used over standard GPT. So ChatGPT is built on top of GPT 3.5, which is one of the versions of GPT. On that, they incorporate this human feedback, questions, answers, human feedback, and they based on that, they tune it to formulate good conversations. So these are the steps of how ChatGPT is formulated. So you collect demonstration data and train a supervised policy. Then you select a prompt from the prompt database. suppose the prompt is, let us say, explain the moon landing to a 6-year-old. And then they look at the answer. Yes, the answer is some people went to the moon. So they have a human who, who evaluates the response of the system and gives the desired behavior, right? So for this prompt, what should be the desired behavior and how well or badly the system has performed, that's a human feedback which is given. And with the human feedback, this GPT-3 is fine-tuned with supervised learning. So this is the incorporation of human feedback into the original large language model. So this is the first step. Then the second step, in order to, human is not editing. This is a better answer. It gives the, yes, not just, This is where, you want to, in the step 2, you have multiple model outputs, right? So you have multiple actions. So you have multiple prompts. Is the system, given the user input, the system has generated different prompts, and you want to know which one has performed well. So the human labeler will rank these outputs. So suppose there are 4 prompt generators, or 4, and they have given this, so human will rank the output. And this is also used to train the model. And that is where reinforcement learning is used. Right? So this is action 1, action 2, action 3, action 4. Why is reinforcement learning? Because you have a conversational system, which is not just a single interaction, which is multiple interactions. So you look at, in this interaction, which one is better, and so on. In the third step, you optimize a policy against the reward model using reinforcement. So you sample a prompt. So you have, suppose, 4 models, 4 strategies. Out of these 4, you sample 1. And from that policy, you get the output. And the reward model calculates a reward for the output, and you update the policy, right? So your policy can give strategy 1 or strategy 2 or strategy 3. So you take one strategy, and then you get the, whether the task was accomplished or not, you get the reward. So use reinforcement learning with human feedback to tune them. So on top of the standard large language model, ChatGPT, which was initially called Instruct GPT, use this instructions and human feedbacks to, in different steps. The first step, you try to give the correct answer. You look at the model answer, try to give the correct answer, let the model tune itself. Second step, different strategies, the human, ranks the strategies. And the third, use reinforcement learning. So this was what was added to these large language models to get these types of data. Now, if you come to the domain of, biomedicine, of medicine, this has also caught up quickly. So if you want to develop large language models for medicine, reinforcement learning with expert input is very important for achieving accurate and unbiased work. What we understand, what I understand, is the domain of medicine. Getting the correct output is extremely important in many domains. And therefore, instead of just looking at the answers, you want to correct the answers. So you can collaborate with medical experts who have agreed to a relevant, etc. And then you use the expert feedback to help guide the model's learning process. So these type of reinforcement learning involving human experts are being used for developing specific LLMs in the domain of medicine. So just to sum up, we have general purpose LLM, We have task-specific models trained from scratch. We have general purpose models, then trained with the domain, and so on. For example, in January 2023, Microsoft launched this BioGPT, which is like a chat GPT of life science. That's how they positioned it, right? And they have specific tasks and prompts from which they do train using the chat GPT type of methodology. So this is one of the successful language models which is introduced. And in the paper that they brought out, they made the following observation. So they studied the prompt design, target sequence design when applying BioGPT. And they found out that, if the prompts are designed with natural language, they work better than giving structured prompts. So for training BioGPT, they use different pre-text tasks such as question answering, document classification, text generation, relation extraction in the biomedical domain. And they found that BioGPT achieved the state of the art in 3 different end-to-end relation extraction tasks and 1 question answering task over the original model. So this is the original GPT model, and this is BioGPT, which is built using reinforcement learning on this model. This is just a slide to show how BioGPT, what is its performance in the PubMed QA domain. So the large version of BioGPT achieves 81% accuracy. This is the smaller, and this is human performance is 78. And these are some other languages people have used. Okay, so this is the last slide. What is happening today in this domain? This is taken, May 2023, MedCom, different language models, how they are being used. So with this, I'd like to stop if you have any questions.